Okay, so let's have a look about how we can do work in physics with the normal sort of situations that we can have a look at that'll appear in questions. Okay, so remember that it's the force times the displacement times the cos of the angle that the force is acting on. So here we've got an object here. Okay, look, here's the formula. Work equals the vector force times the displacement in the direction of the vector. That's why the little arrows are there. But we use it as F delta x cos theta, force, displacement, the cos of the angle between the displacement and the direction of motion. So this is the simplest case here. We've got an object here and we push it with this force. Can you see this arrow is the force, and it ends up over there. So the object is moving like this, the force is moving like this, and this object has displaced from over here to over here. So that's my delta x, the displacement from here to here. Okay, so you can see here the force and the displacement are exactly in the same plane. So this cos theta, the angle between the force and the displacement, is 0. They're in exactly the same line. And the cos of 0 is 1. Okay, so when we do this, this is called doing positive work, because the force has increased the energy of the system. You just had this block sitting here, and all of a sudden it was moving, and it was moving in a direction. There was motion, so it's now increased the energy. So this would just be the force times the displacement times 1, because the cos of theta is 1. So this is the simplest situation. Then, for instance, if you've got this object here, and you move it from over here to over here, but you do it with this force over here. Can you see this force over here? This force has got an upward component and it's got a horizontal component, okay, or a component in the direction of the displacement. So we can call this angle beta, because we need to discuss how this is going to work into the formula, okay? So if the force and the displacement are at an angle beta to each other, the force in the direction of the displacement is just the component, okay? So the upward force is wasted in this work situation. I know it's different in Newton's laws, but this is work and not Newton's laws. So the upward component we're going to completely ignore, and the only part of this that we're interested in is the horizontal component, because this object displaced from here to here. So if you look at the x component, it's going to be F cos beta, okay? If we look at the formula here, we say the work is done by the x component of the force cos the angle, okay? But now, because we're looking at the x component already, then this this displacement and the x component are in the same direction. Sorry, hang on. So it then becomes the work is the x component cos theta times the displacement, because this cos beta is now incorporated into this fx. So it's confusing, okay? This is how the textbook explains it. So the way I like to think about this is resolve the forces, and whatever the net force is, you multiply by that, and then the theta is automatically 1. So here, the moment you look at this formula, if you take this original formula, okay, you can then say work is the force times the displacement times the cos of theta. But the only force that is moving it in the x direction, that the only force that's doing work is fx, okay, and then that works out to be F cos beta times the displacement. And then the cos theta has disappeared over here because we resolved this force. If we hadn't resolved this force, we would be using it. So, okay, so now look in this situation here where you've got this object here and the displacement is this way. Okay, here's the object and we want to displace it that way. This is like the lady picking up the bag on her back. The force is upwards, the displacement is this way. Okay, so theta over here is 90, the cos of theta is 0. So this force over here is doing absolutely no work on this object. So force is at 90 degrees, no work. Now what happens? And this is friction. This picture is all about friction, okay, because friction opposes motion. So if we have this object and we're displacing it that way, but the force is acting the other way, they're in opposite directions. Can you see here? The displacement this way, the force that way, this angle over here is going to be 180 degrees. And the cos of 180 is -1, okay? So now this force is doing negative work, and it is decreasing the energy of the system. Because this object is displacing this way, the force is acting oppositely. So the maths says the cos of 180 is -1. So basically, this works out like when we do force diagrams, you know that you subtract forces that are in the opposite direction because forces are vectors. So in terms of work, they make you express that angle between the forces, but you would already know this yourself, because if this object's moving this way and there's a force going that way, you subtract this force instead of adding it. But this cos 180 equals -1 is how this works in work, energy, and power. Okay, so now we come to the situation where we've got an object on a slope. Okay, so here's my object on a slope. It's going to want to displace down the slope that way, because all objects want to slide down the slopes. And what is pulling it down the slope? The parallel component of the force. Okay, so only the parallel component of the force is considered here, and this parallel component of the force then is Fg parallel, okay, which is Fg sine theta. We can ignore the normal because it's not doing any work here. So if this object slides down the slope, the work done by this force will be Fg delta x cos theta, and cos theta will be 1. But now, if there's another force that we can't see in this picture that's pushing this up the slope, the weight is still acting down the slope. It's going to become cos 180 because the object's moving up the slope and the weight goes down the slope. So this angle here is 180. So then this force is negative. So, I mean, we would do this anyway in Newton's laws. We would subtract this force. But here is telling you the work done by this force, how to calculate the work done by this force. So now, this is a more normal situation. There's more than one force on the object. So here you're just going to work out the components of the forces, put them in a straight line and add or subtract them and find the net force, okay? And the net force is the only thing that's doing work. So if you have a look here, here's this force this way, okay? And there's this force that way. Here are the components of this force here. So the net work will be the net force times the displacement times the cos of the angle, okay? And so the net force is going to be Fx minus Fs because they're in different directions. This question is assuming to the right is positive. So this force F, its x component, this little red thing here, is positive. And then this Fs, static friction, is negative. And then you can multiply it by the displacement, however far this object moves to the right. And then this cos theta is going to become 1 again because we've considered the motion here. So this thing here irritates me in this equation, because if you found the net force in the direction of motion, then cos theta automatically will fall away. So if you wanted to resolve them, Fx resolves into F cos beta, this angle over here, minus Fs. Fs is in the plane of motion, so it's fine. So the net work can be calculated by subtracting the forces, multiplying them by the displacement by cos theta. Or you can find the net work by finding, first of all, the work done by this force in one sum, and the work done by this force in another sum, and that will give you the net work. And then because you calculated the work with the cos of theta, this one, if this is the direction of motion, this will be a positive value, and this one, Fs, is at 180 degrees to the direction of motion, so the cos of 180 is minus 1. This will automatically subtract. So this formula for the net work is basically an expansion of this. Here we just did the forces and multiplied them by the displacement. Here we calculated one work and another work and found the net work. So I think this one's better, to always work out the net force before you multiply it with the displacement. But that's just my opinion. Okay. So let's leave this here like this before this gets too long as well.